All right, so the second review that I'm going to do really quick is a little bit about water potential, solute potential, osmosis, diffusion, active transport, all that stuff. So as far as the math goes, there's really two formulas that they give you on the AP exam. One of them is this one to calculate solute potential, and then this one, which is to calculate water potential. Your final answer to all of this stuff is going to usually be your water potential. That's usually what they're looking for. And basically what you need to know is that the more negative this number is, that means water is going to go towards that side. Water is going to go towards the side that has the lower water potential. But water potential is determined by two different things. What we're used to doing are these problems where you have a cell and maybe it's 3 molar inside and 1 molar outside. And if we were only looking at this and nothing else, we would look at this and we would say, oh, well, water's going to go always towards the hypertonic side, and that would be inside the cell. It's more concentrated, hypertonic, and so this cell would swell and maybe lyse. But there's a second thing involved. We know that plant cells, for example, in this situation, if this was a plant cell, it has a cell wall around it, and water would enter, but the cell wouldn't lyse. At some point, the water would basically be going in and out at equal amounts, but that doesn't make sense, because if we're putting, let's say, this into pure water, you would say, well, water should always be going in. It should be trying to dilute that. But there's a second factor, and that's the factor of pressure. If we have enough pressure on this, it's going to prevent more water from coming in. Pressure is going to actually, make water go one way or the other, or prevent water from moving one way or the other. And so that's why water potential is not just based on molarity, but it's also based on pressure. We can also think of it this way: when you have one of these YouTube problems, if you actually had a plunger and you're pushing down on this side, that's obviously going to put pressure on the water, and you can imagine it sort of forcing it through this semi-permeable membrane if water is able to flow through, even though solute-wise, water might tend to naturally go towards the left side. Okay, so for these problems, if they're asking, this is a really easy problem, really. They're giving you the solute potential, they're giving you the pressure potential, and that's inside a cell, and then they're giving you the solute potential and the pressure potential outside a cell, and all they're asking you to do is basically calculate the water potential on each side, and then determine which way the water is going to go. So if you do this, I believe you get negative 2.5 inside the cell, negative 4.5 plus 2, and then negative 4 plus 1 gives us a negative 3.0 outside the cell. So since the outside is more negative, the water would tend to flow out. The other thing that you may be asked to do is to calculate the percent change of something. And the thing about percent change is it's not a formula on the formula sheet. They're expecting you to know it. So the percent change is going to be final minus initial over initial and then times 100. It can be a negative number. For example, here, a bag originally weighed 2.5 grams. At the end of the experiment, it weighed 1.8 grams. That means this bag lost weight. That means that the percent change is actually going to be a negative number, and that's okay. So we would do for this final 1.8 minus initial, which is 2.5, over initial, which is 2.5, and then you multiply that times 100. And then for the second one, you're actually going to get a positive number because this bag gained weight. So that one's going to be 8 minus 5 over 5, and then times 100. If you calculate it out, you get negative 28% for this one, and for the second one, you get 60% gain. All right. This graph, you see this all the time. Sometimes they'll ask you to make this graph from percent change data. So this is the graph where here is the 0 point. This represents bags that gained weight, or potatoes that gained weight, and this would be lost weight. So these are percent changes, positive and negative. The idea is when you graph this, these are your increasing molarities. When you graph it, you want to see where it crosses the x-axis, because that would be your estimate of what would have been an isotonic solution for the potatoes. They technically shouldn't have gained or lost weight at that molarity. So for this particular one, that molarity is 0.3. Now, what use is that? Well, when they're asking you to calculate water potential, or solute potential, I should say, it's negative ICRT. Okay, I is the ionization constant. It has to do with how many ions something breaks into, or how many particles it breaks into. In this case, they say that you're using sucrose, so I is just going to be 1. And that's the case if it was glucose, sucrose, starch, anything that's not ionic. If, on the other hand, they gave you something like salt, NaCl, now this would actually break into 2 ions. Or I could give you, for example, let's just make one up, aluminum chloride. This would actually break into 4 ions, 1 plus these 3. So that's all the ionization constant is for. Usually it's going to be 1. A lot of times these experiments are with glucose, sucrose, starch, something like that. C is that molarity that you just calculated here. So C is really the only thing that you actually have to use the graph for, and that in this case was 0.3. R is a constant. They provide that for you, 0.0831. And then temperature has to be in Kelvin. They even tell you that on the formula sheet. So our temperature was 30 degrees Celsius. We would add to that 273, and that would give us 303 Celsius. It's going to be negative. And when you calculate that, you get negative 7.55 bars. By the way, on numerical ones, they're always going to tell you what to round to. They'll say round your answer to the nearest hundredth, or round your answer. So you don't have to do any of that stuff you have to do in chemistry with, you know, what rounding and how many significant figures are there and all that. In this case, they also give you the pressure potential as being 6.2, and then they want the final water potential. So you've calculated here the solute potential, so this is just going to be negative 7.55 plus your pressure potential of 6.2, and you end up with a final answer of negative 1.35 bars. So most important thing here is knowing how to get C from your graph. If they ask you to graph it, or if they give you a graph and ask you to interpret it, or if they just give you percent changes. I did this on your midterm. Some people had no idea what to do with this. You were just given percent changes. So the molarities were, 2, 4, 6, 8, 10. And then the percent changes were, let's say, 25, 18, 10, 2, negative 3, and it kept going. And so basically what you should have done is to calculate C. Instead of graphing it, I asked you to estimate it, and you would just look for at what point between which 2 molarities would this have gone from a positive number to a negative number. And since this would be between 8 and 10, typically anything would have been acceptable as far as 9 or 9.2. It wouldn't matter. If you gave me something that was between 8 and 10 as your estimate, I would have accepted it. I'm not going to go over this page. You guys can look up these words. Cell membrane, I'm not really going to go into either. I will just make a couple quick comments about it. We talked about it in class. Number 1, this is cholesterol, which is a steroid. Only in animal cell membranes, not in plant cell membranes. But what it does is it helps to keep the fluidity of the membrane, keep it fluid at low temperatures. Unsaturated fatty acids do the same thing. Remember, they cause kinks. The double bonds cause kinks, and that also helps it to remain fluid. Remember that these are your fatty acids and that they're hydrophobic, that the heads are hydrophilic. And the only other thing, remember, proteins have lots of functions. This could be a transport protein, for example, because it goes all the way through the membrane, so that would make sense. On the inside, you could have proteins that are structural proteins that maybe are connected to the cytoskeleton to hold the cell shape. And when you see a protein like this, not a very good drawing, and these are supposed to be sugars, oligosaccharides, this would be a glycoprotein, and glycoproteins are usually ID markers, which are going to identify a cell as belonging to you. So that's a little bit about cell membrane. These YouTube experiments, I gave you guys a couple of examples in class, but I'll give you some here. Let's just say that A was the only thing in here, and A could pass through the membrane. One side is going to be hypertonic to the other side. The other side is going to be hypotonic. So if we pretend like A was the only thing that had been added here, we would say that side A is the hypertonic side. Or even if everything is in here and you were asked what is it with respect to just A, we would say side 1 with respect to just solute A is hypertonic, more solute than side B. If A can pass through this membrane, which way will it go? Well, it will always go by diffusion, random molecular motion. it will tend to go from where there's more to where there's less. That's the definition of diffusion. And so A would tend to go to the right. On the other side, on the other hand, if we were just looking at Z, we would see the opposite. Z, we're actually hypotonic over here with respect to the other side, as far as just Z goes. And if Z could pass, Z would go the other direction. It would go from where there's more to where there's less. In class, I gave you an example. I said, well, what if you have both of these in here? Would side A or side 1 overall be hypertonic or hypotonic? So if you total everything, we have 30% here, we have 46% here, so this side would be the hypertonic side. And let's just say that, that A can pass and B can't. Well, we already said that A would go towards the right side. The other question that you can be asked, which really throws people off, is which direction would water go? And the thing you have to remember about water is that water also, by osmosis, is going to tend to move from where there's more to where there's less. Water is always going to go towards the hypertonic side. So if we look at this, side B, remember ignoring all this stuff, was overall hypertonic, or side 2, to side A, side 1. That means that, and then if A goes this direction, that actually is going to make it even more hypertonic than it was before. So water's going to go towards the hypertonic side, and so water would go up on this side, and the water would go down on this side. And so that's what would happen in this particular situation. Then I gave this example in class, and I said, what if there was 10% starch in this bag and starch could not pass, and everybody knew that this would be hypertonic inside, hypotonic outside, and water would tend to go in. Then I said, well, what if you had the same situation over here and you had 10% starch in the bag and starch cannot pass? In this case, the inside is hypotonic. It has less starch than the outside does. Don't get confused here with which direction water's going to go. Remember, if you just memorize water goes towards whichever side is hypertonic, water's going to leave this bag. If you wanted to figure it out a different way, you would say, well, water's going to go from where there's more to where there's less. If there's 10% starch, the remainder, the other 90% in here, would be water. Therefore, water's going to go out because there's only 80% water outside and there's 90% water inside. So that's a little bit about that. All right, and I'm going to do energy next.